Hello students, today we're getting back with another video lesson 24. In today's video lesson, we'll learn about terminal velocity.
Terminal velocity is the maximum velocity attainable by an object as it falls through a fluid, that is air or liquid. Let's go and try to understand what is this terminal velocity all about. For this, let's consider a large column of liquid contained in this cylindrical beaker, or let us allow a spherical body to fall through this column of liquid. Now, initially, this spherical body will accelerate downwards. Why? Because it has got some mass and the gravity is trying to pull it towards the bottom of the container. Now, as it falls down, its velocity keeps on increasing, but after a certain point of time, it becomes constant. Why? It's all because as it is flowing through this liquid or through this fluid, a drag force acts on this spherical body, which is against the direction of velocity of the spherical body, which try to oppose its motion, and hence it tries to maintain a constant velocity. This constant velocity is called your terminal velocity. So we will go further and try to find out what will be the expression for this terminal velocity. Let's consider this container containing a column of liquid. Let's consider a spherical object falling down through this liquid column with terminal velocity Vt. Let r be the radius of this spherical body, rho be density of the material of this spherical body, sigma be density of the material of the fluid. That means sigma is the density of the fluid material through which this spherical body is flowing. Eta be the coefficient of viscosity of the fluid. Now, since this spherical body has got some weight, and this weight of the spherical body will always act downwards, which is given by W equals to mg. Now, what will be the exact value of this weight? Let's find it out. So W is equal to mg. Now m is what? Mass, and we know mass is volume into density multiplied by g. Now, since the body here is a spherical body, so the volume of the spherical body will be 4 by 3 pi r cube, volume of a sphere, multiplied by rho, that is density of the spherical body, into g. G is acceleration due to gravity acting on the spherical body at that point of time. Now, as this spherical body is flowing through this liquid column, it has displaced some liquid around it, and we know that from Archimedes' principle, there acts a buoyant force, and this buoyant force will be equal to the amount of liquid displaced by the body which is immersed in the fluid. Hence, this buoyant force will apply an upward force, which we call it upthrust, in upward direction. So let's find out what will be the value of this upthrust force. the value of this upthrust force will be the amount of volume, or let's say amount of weight displaced by this spherical body. So the upthrust will be 4 by 3 pi r cube sigma g. Now why sigma? Because the spherical body is displacing the liquid. So the amount of liquid displaced will be given by sigma here. Now as the liquid is flowing down through this fluid, a opposite force acts on it, and this force is called your drag force. Now we have studied about this drag force in Stokes' law, and we know that whenever an object flows through a fluid, a opposite force acts on it, and this opposite force is called your drag force. And for a spherical body, a drag force is always given by 6 pi eta r vt. Now at terminal velocity, the weight of the spherical body will be equal to u plus fd. That is, the weight of the spherical body will be balanced by the two opposite forces, which is your upthrust and drag force Fd. The weight of the body is given by 4 by 3 pi r cube rho g, whereas upthrust is given by 4 by 3 pi r cube sigma g plus the drag force 6 pi eta r vt. Now on simplifying, we have 4 by 3 pi r cube rho g minus 4 by 3 pi r cube sigma g equals to 6 pi eta r vt. Now from the left hand side, we can take 4 by 3 pi r cube g common. So on taking this quantity common, we have 4 by 3 pi r cube rho minus sigma into g equals to 6 pi eta r vt. Therefore we'll get vt equals to 2 by 3 into r square rho minus sigma g divided by eta. So this is our required expression for terminal velocity. Now there's important thing to note from this terminal velocity. Number one is Vt is directly proportional to radius square, which means that larger the radius of a spherical body, more will be the terminal velocity of it as it flows down through a fluid medium. That is why the velocity of bigger raindrops are more as compared to smaller raindrops. Number two is that terminal velocity is directly proportional to the difference between the density of the spherical body and the fluid through which it is flowing. So from this we can derive two conclusions. A is that if rho is greater than sigma, then terminal velocity will be positive and the spherical body will fall down. What does it mean? It means that if the density of the spherical body is more than the density of the fluid, then in that case the spherical body will flow down the fluid very easily. Next, point number B is if sigma is greater than rho, then the terminal velocity will be negative and hence the spherical body will rise up. It means that if the density of the fluid through which the spherical body is flowing or falling down, the terminal velocity will be negative, and if terminal velocity is negative, instead of falling down it will rise up. That is why you will always find that air bubbles inside a liquid always rises up, since they have less density as compared to the liquid in which they are forming. Now, the most common example you can see is clouds. When the clouds becomes heavier, they come towards the come closer towards the surface of the earth, and when the density of the cloud molecules are less, then they rise upwards. So this is all about your terminal velocity.
With this, we come to the end of our today's video lesson. I hope you have understood this. Thank you.